Stuck. Testing. So we're live, but class is still about to start. So hang in there, people who are watching live. Okay, shall we start? Shh, let us begin, let us begin. Am I mic'd? Can you hear me? I can never tell if I'm microphoned or not. Hear me in the back? Okay, now let's mess with the lights. Is that better or worse? Who says worse? Worse? All right, better? All right, sure, we'll try this way. Well, you know, for the people watching online, maybe it is better. So look, I've got like 3 computers here now, so hopefully it won't screw up. So right now, that one is broadcasting. Okay, so today we have the first of the lectures that maybe might give some people some problems. So it's one of those topics that is either it looks really easy but it's actually hard, or it looks really hard but it's actually easy, and I don't know which it is. So I'm going to like talk really slowly, and hopefully you'll follow along, because if you get lost today, it'll be kind of hard to catch up later. So try to follow along. Some key concepts today if you've never seen them before. And if you're sort of okay, do the homework and it'll probably be clearer. So we're talking about the things that are relevant for you to assess your MCATs and your LSATs and your GMAT scores and things like that. So essentially rankings and measurements of diversity and variance and things like that. So all characteristics of this thing called the normal curve, which really defines the foundation of basic frequentist statistics. And by the way, I say frequentist statistics because it's based upon this frequency distribution idea. Much of what we consider to be traditional statistics that you'll come across in pretty much every class you take these days is frequentist statistics. There are assumptions about probabilities, about distributions, about how often things occur. But I will plant a little caveat for you that in the really advanced halls of high-powered science, people are using frequentist statistics less and less. They're using something called Bayesian statistics more and more. And we won't do that in this class, but I will talk about it in a few weeks just to introduce the idea of it, and maybe it'll excite you if you end up going on into quantitative methods in your career. But be aware that right now, frequentist approaches are the standard, even though they may not be the best way. And the idea behind a frequentist approach is things tend to be distributed in the population a certain way. And most often they're distributed in this normal way, this Gaussian way, this bell curve way. Okay? Pretty much every human characteristic, I've said before, is distributed this way. There's always going to be a lot of people who have the central characteristics, and fewer people who have more extreme characteristics, and it tends to be shaped this way, or some variation thereof. So let us move on. Last time we covered measures of central tendency. Central tendency is this attempt to find a number or a statistic that summarizes our distribution. Most commonly we have this thing called the mean. We've all had means before. Your average mark in class, that's your mean. The median, we all know that is, and mode, of course. So the 3 major measurements of central tendency. And we looked at 2 measurements of variability. And someone after class asked me what the difference between the 2 is, so I'm going to make sure we understand that. Again, central tendency is an attempt to measure the typical response in our sample. And there are different ways of measuring typicalness. It could be the most common response, it could be the middle response, it could be the mean response. So central tendency is typicalness. Variability is diversity. So how wide my distribution, how much it varies from that typical response that I tried to measure. And we looked at 2 main measurements of typicalness, or rather of variability. We looked at range and interquartile range. Range is fairly obvious. Range is the distance between the lowest number and the highest number, so the actual physical width of my distribution. And the interquartile range was a bit more difficult to understand, but I gave you a formula for it. So it's when you subdivide your entire sample into equal bits of 4, and you take the middle half, really. That's your interquartile range. The difference between this Q1 and Q3, we call it, and Q2 is the median still. So the formula I gave you, if you remember, gives you the rank of the number of the cutoff, not the actual Q1 and Q3. It gives you the rank. You've got to convert the rank to the actual number in your sample. Right, so and try the homework. If it's not clear, come see me. We'll talk about it more. So today, we're going to look at 2 more measurements of variability. Standard deviation and variance. We're not really going to look at variance, because variance is something that's mathematically interesting that will be used later on for inferential statistics, and it's hard to really conceptualize, but the standard deviation is relevant right now for this basic kind of exploration. And those 2 are kind of the same thing in that the variance is just the square of a standard deviation. So once you compute one, you can compute the other one. I'll say it again. Standard deviation squared is variance. Okay, I showed you. Oh, hang on. Here's the textbook talks about standard deviation as being SD. Okay, that's kind of a modern way of looking at it. Most traditional statisticians use sigma to indicate the standard deviation of the reference population. What do we call measurements in the reference population? What's the term for things there? Remember, is a word begins with P. You've forgotten already? Okay, let's back up a bit. So, a parameter, exactly. So I'm backing up by saying, when I'm trying to infer things from a sample, I have my sample of people in my study. I'm doing things to the sample to make inferences about a reference population. If I'm taking the average age of this class and trying to figure out whether that's representative of the average age of the university, the class is my sample, the university is my reference population. Things I do to the class are statistics. Things I do with the reference population are parameters. So sigma here is a parameter. It's the standard deviation in the reference population. There's another symbol we use for the standard deviation in the sample, and that's a small s. I'll show you a summary of that in a second. The textbook, for some reason, uses SD for both of those, which is confusing. There it is. So the standard deviation, or sigma, tries to tell us how much the data in our sample varies, how different it is from each other. And it's based upon something called a deviation. Now, a deviation I mentioned last time is just the difference between the mean and any individual score. You just subtract the mean from that original score. So before I give an example, here's our standard, our normal curve again. And the power of a standard deviation is this, is that the difference, the distance between one standard deviation and the mean, and either direction combined, constitutes 68% of all the data. 2 standard deviations from the mean constitutes about 95% of all the data. 3 standard deviations from the mean constitutes 99% of all the data. So regardless of what my data is, regardless of what the numbers are, regardless of where I've sampled it, assuming that it's normally distributed, these facts are always true. 1 standard deviation, symmetrically, constitutes 68%, 2 constitutes about 95%, and 3 constitutes about 99%. This is a powerful fact that we're going to use in some other calculations later on. All right, so if I give this class a midterm, and maybe you guys score really highly, I give another class a midterm and they score really poorly, it doesn't matter what their scores are. The standard deviation in each population is going to have the same relationship here. 1 standard deviation will be exactly 68.2% around the mean, 2 standard deviations be exactly about 95%, and so forth. That's the fact we have to keep remembering here. So in other words, about 3 standard deviations in either direction of the mean pretty much encapsulates almost all of our data, about 99% of our data. So here's an example. Here is 10 students and these are the weights, so 10 students in pounds, so 110 pounds, 120 pounds, 90 pounds. What's the mean? The mean is you add them all up and divide it by 10, and we get 150. Okay, a deviation will be the difference between 150 and each of these numbers. That's how much each value deviates from the mean. Okay, so for the lightest person, 110, the deviation is the mean minus 40. Minus 10, 110 rather, which is 40. For the heaviest person, it's the mean minus that number, which is that. So it's going to be plus or minus a certain number. So a deviation is how much each data point deviates from the mean. For the first data point in that sample, it's minus 40. For the last one, it's plus 40. What's a standard deviation? Standard deviation is the typical deviation in our sample. Because each data point has a different deviation from the mean, we're looking for a way to estimate the typical deviation. Now, if you're thinking creatively, you realize that by computing all these deviations, I have another data set now. I have my data set full of weights, but now I've got a data set full of deviations. And maybe that data set full of deviations is also normally distributed. Maybe there's a mean to that as well, and another deviation. Yeah, it's true. We can go on forever. Okay? That's part of the magic of all this. So what we're looking for here is some kind of measurement of the typical deviation in my set of weights over here. So this is the data again. I'm re-summarizing it. My mean is 150. 110 minus 150 is minus 40. 120 minus 150, minus 30, and so forth, and so forth, and so forth. Notice that these two values are exactly the mean. It's not always the case, but in this particular sample, they are exactly the mean. So it's 0 and 0, and so forth, and so forth, and so forth, and so forth. Okay, and that's my total. My total is 0. Is that a coincidence, the total is 0? No. Because, mathematically, if I've defined my deviations as the difference between each sample set and the mean, if I add them all up, I'm always going to get 0. So, what's the mean deviation then? If I take the mean of all these numbers, what do I get? 0. It's always going to be 0. How is that useful? It's not. It's not useful because these positive numbers will cancel out the negative numbers. So I need a different way to estimate the typical deviation. I can't just take the mean. So distribution, the sum is always 0. Therefore, we're going to square it. We're going to square these numbers here. Why do you think we're squaring them? Are you familiar with using squares in math? Yeah. Get rid of negatives, exactly. It's the only reason we're doing it. So there's a little trick people always use in deriving things in mathematics. We square them so the negatives go away, and this is the equation. Standard deviation is the sum of all the squares of all the deviants divided by n minus 1. Now, that gives us sort of the mean of the squares of the deviants, but it's not n, it's n minus 1. N, by the way, is always the label for the total number of things in our sample. If it was the mean, it would be the squares divided by n. But it's the squares divided by n minus 1. And this is something you'll come across all the time in these formulas. It's kind of messes with your mind a bit. I won't go into the reasons why it's n minus 1, except it's called a Bessel correction, B-E-S-S-E-L. The book won't tell you this, but this is the formula for the statistic of the standard deviation. The statistic, again, is the standard deviation of my sample. The parameter of the standard deviation is a standard deviation of the reference population. The formula for the standard deviation of the reference population doesn't have the minus 1. It's that squared, sum of the squares divided by n. When we move down to the statistics level, so the sample level, it's an n minus 1. So I won't go through the derivation of that, but Bessel, famous mathematician, figured out that samples introduce an error, and the way to correct for that error is to reduce the total number by 1. All you need to know to do these questions is that for your sample, the standard deviation is the sum of the squares of the deviants divided by n minus 1. For the parameter, it's the sum of the squares of deviants divided by n. Okay, so here's our example again. Here are our weights. Deviation scores again are this, right? The squares of these are going to be 1600 and so forth. We add up all the squares and we get 6000. The standard deviation for the sample, which is the statistic, is 6000 divided by n minus 1, which is 9. And take the square of all that, we get 25.82. So that is the standard deviation in my sample. That tells me is that typical distance between each member of my data set and the mean is 25.82. Right? It varied from minus 40 to plus 40, but typicalness is 25.82. How are you define typicalness? So, about notation again. I mentioned that sigma is a standard deviation in the reference population, or the parameter. S is standard deviation in the sample, or the statistic. Okay. Still with me? All right, good. I'm speaking like your kindergartners, I know that, but sometimes I got to go slowly to make sure it all gets absorbed. All right, so once again, the standard deviation gives us a standard or a typicalness of the amount the deviation scores differ from the mean, and it tells you how wrong, on average, the mean is as a summary of the overall distribution. Because if my standard deviation is big, it means I've got all kinds of splay in my data, and the mean is in the middle of all that, but it's all this variation over here. If it's small, it means my distribution is quite narrow, and my mean is probably quite representative of that narrow set. Okay. Now I mentioned there are about 3 standard deviations above and below a normal distribution. That encapsulates 99% of my data. Keep that in mind. Here's that curve again to remind us. This will come up again and again and again. So a person who scores 1 standard deviation below the mean is about, what's that, 2.3% plus 13.6, that's about 16%, 15.9% above everybody else. So let's say this is your midterm mark. And I don't tell you what the scores are of everybody else. I don't tell you what the mean is. I just tell you that your mark, you got 1 standard deviation below the mean. What you can compute from that is that you scored 16% higher than everybody else. You were in the bottom 16%. In other words, there's 16% of people who are below you, and about 84% that are above you. If you scored one standard deviation above the mean, you're over here, right? So here you've got about 84% of people below you. That's a percentile. You've heard that term before. We're going to do percentiles in a second. It doesn't tell you what your score is. It tells you where you are relative to everybody else. Okay. So the advantages of using standard deviation is that we're using every single data point to compute it. Remember we looked at interquartile range and things like that. We weren't using all the data points, we're using certain selective ones. This uses all of them. So it's a bit more representative, one thinks. It's more stable than the IQR. What does stable mean in this case? Remember I defined stable last time. Nope. Yeah, well, it's true, but that's not what it means though, yeah? That's right. So if I take it here versus another class and so forth, I'm probably going to get very similar numbers. Whereas range is going to be different wildly between different samples. That's what stability means. It's useful, as we'll see later on, in doing other kinds of inferential statistics. We're going to have to compute the standard deviation for a lot of different things. And it's useful for figuring out your rankings if, in fact, the data is distributed normally, as we tend to assume. So disadvantages are, like the mean, it can be influenced by extreme outliers. Because it's all about the width, again. If you got one guy who weighs like 500 pounds in the class, he's going to pull the standard deviation that way. And it's not intuitive. Obviously, it's not intuitive because some of you are looking at me like, what? It's not intuitive, so it's a disadvantage. Whereas the range is intuitive. So variance, I mentioned, is just the square of a standard deviation. So in the example I just gave you, a standard deviation was 25.8. The square of that is 667. It's not as easily interpreted. It doesn't have a real world representation. When I said the standard deviation was the typical distance from the mean, In the case of the example I just gave you, it's in pounds. So typically in my sample, the typical person was 25 pounds heavier than the mean. If I square that, what does square pounds mean? It doesn't mean anything. It's a mathematical kind of construct. It doesn't have any real meaning in the real world. It has a mathematical meaning. So that's why it's a little problematic. We won't go into it right now, but it's useful again in computing other things. So once again, sigma is the parameter for standard deviation. S is the statistic for standard deviation. Sigma squared is the parameter for variance. And S squared is the statistic for variance. And for some reason, again, the textbook uses SD for both of these and SD squared for both of these. So be aware of that. And I tend to rely on this because this is the classical way of writing things. And I want you to be aware of them too, because as you progress through life, you can't rely upon your textbook's notation. You have to rely upon what the rest of the world says too. Okay, variance is just that in the population, in the reference population. It's just the standard deviation without the square root sign. By the way, everyone understands what these symbols mean, right? No one's unclear what the summation sign is. You've seen it before? Right? If you don't, just come see me later. We'll discuss it. That, remember, is the mean in the reference population. That is a total number of people in the reference population. And this is the deviation. Right? And in the sample, it's n minus 1. That's the only difference here. Okay. Again, to summarize, depending upon the kinds of measurement scale your data is in, it determines what kind of measurements you can use. So again, if you have nominal data, which is like the place you were born, or your name, or things like that, things without rankings attached to them, you can measure the mode, that's about it, and you have no measurement of variability. If you've got ordinal measurements, which are things like rankings, where your ranking is in class, you can measure a median, you can compute range and IQR, and for everything else, you can compute a mean and compute a standard deviation and variance. And that's more powerful for doing other kinds of statistics, as we will see. So let us move on now to this thing called relative standing. We've already touched upon it when I mentioned that if you get one standard deviation below the mean in your midterm, it means that you're better than 16% of the class. That's a relative standing. That's a standing of where you are relative to everybody else. So we're going to look at two kinds of relative standing measures, percentiles and standard scores. Percentiles, you probably know already, is the percentage of people you did better than. Standard score is really just a z-score, which is really just a standard deviation. So we kind of use these terms interchangeably. So remember that. Standard score is the same as a z, the same as standard deviation. We'll look at that in a second. Again, it seems kind of confusing at first when you stop and do them. This is nonsensically basic math. For some reason, we tend to present it in a complicated fashion just to make your lives miserable. But try to cut through the nonsense and just see the basic math aspects of it. So we've done quartiles already. Remember, the quartile is when you divide up your sample into 4 equal bits. So the first quartile is the point at which 25% of my data is below. The second quartile is a point at which half of my data is below. What's the other word for the second quartile? You have another word for it. Q2, also called median, exactly. And the third quartile is the point at which 75% of my data is below. We have this thing called deciles. Deciles is when I'm, instead of dividing into 4, I divide into 10. So the first decile will be the point at which 10% of my data is below. And the second decile will be the point at which 20% of my data is below. Are below, data is plural. You know, we tend not to use deciles a lot, but it's there. And percentiles is 1/100th of the distribution. So the first percentile is the point at which 1% of my data is below, and the second percentile is the point at which 2% is my data is below. So if you score 84th percentile in this class, it means 84% of the class is below you. It doesn't mean you got a mark of 84. It just means that 84% of the class is below you. If I'm a really hard marker, maybe you got like 60% of the class. But that's actually one of the top scores, and 84% is below you. That's why we use relative rankings. It takes into consideration the differences in the kinds of grading scales people apply. So if I'm comparing your behavior to another professor's class, and maybe he's a much easier marker than me, and his class has really high marks and you've got really low marks, but in fact you're doing better than them because you're better than most of the other class. And everyone in his class has 90%, so it doesn't mean anything. So we compare the rankings rather than the actual marks. That's why we're doing this. Relative standing is a measure of ranking rather than actual scores. So with a relative rank, we can take a score and compute a percentile. We can take a percentile and get the score. The score is what you got on the test, let's say. Okay. So one of the things that we can compute with percentiles is outliers. So we define outliers as either being mild or extreme. We mentioned outliers already. Outliers skew our data all the time. If I'm measuring your weight in pounds and there's someone here who's horribly anorexic who weighs 20 pounds, or someone who's like really obese and weighs 500 pounds, they're going to skew the average. So I need to be able to determine who is an outlier. How am I going to define outliers? And it's not talking about that ridiculous Gladwell book. That's not what we're talking about. We're talking about observations that are distinct and quite different from everybody else. How do we define it? In this course and the textbook, an outlier is defined as any value that is more than 1.5 times the interquartile range. Right. Now, that's any outlier. An extreme outlier is further than that. So an extreme outlier is anything that is 3 times the value of the interquartile range. So to help visually appraise whether or not something's an outlier, we use something called a box plot. Has anyone seen a box plot before? Yeah? Good. Okay, so there's one person. So also called a box and whiskers plot. It's a different kind of a graphical representation, immensely popular in population papers. So you'll see this more and more the more you read of professional science. So in a box plot, you can see right away the interquartile range of the data. You can see right away the median, you can see right away the range, and you can see right away which ones are mild and which ones are extreme outliers. You can't see the mean right away, you can't see the variance right away, but you can see these other things that you cannot see in other kinds of plots. Here's an example of a box plot. Also called box and whiskers. These are the whiskers, and these are the box. Okay. Sometimes we do put in a symbol there for the mean, but usually it's not there. So this is the splay of my data. Let's say it's, again, the weight in pounds of people. So here I'll have 0 pounds, here's like 300 pounds or something, and my data points are spewed along here. Between here and here are my Q1 and Q3. This is my interquartile range. This is my Q2, the median. And these are the minimum values and maximum values. Okay. Now, sometimes, let's say. Okay, so this is the traditional way of doing it, where this is the range. The way the textbook does it, and therefore the way this class does it, is that this is not going to be the range. This is going to be the non-outlier numbers. The textbook keeps the outliers outside of the range. So, in other words, the bottom of the box shows the Q1, the top of the box shows the Q3, the horizontal line shows the median, like I said, and the whiskers show what is not an outlier. In SPSS, if you ask for a box plot, it'll give you a circle to show a mild outlier and an asterisk to show an extreme outlier. Here's an example from SPSS. So this is, I don't know, let's say that's age or something. This is your data. Here are the range of data that is not outliers, here to here. This is your interquartile range. That's your median. If there was a mean represented, it would be somewhere over here. And here are your outliers. The circles are mild outliers, and the asterisks are extreme outliers. So SPSS has computed it for you using that definition. 1.5 IQR is mild, 3 IQR is extreme. Okay. So you can see them in histograms too. Like here's a histogram. You can see the outliers here. They're extreme, but they're not as obvious. They're not as well labeled and not as defined as mild or extreme. In the histogram, we can see the standard deviation a little bit. We can see the mean quite easily. Here we can't see the mean, we can't see the standard deviation. So depending upon the graphical choice you make, you have different things being presented. For systematic reviews and meta-analyses, this is very, very common. I'll show you one in a second. And for other kinds of data, that's more common. So this is a meta-analysis. Remember, a meta-analysis is when people take lots of studies and try to derive a summary of all these different studies. This is an attempt to measure the speed of light. And there are 1, 2, 3, 4, 5 experiments that were done. And each experiment used, I don't know, a set of tests where they had some kind of thing going on, and a device was used to measure a photon going back and forth. This is the actual speed of light. We put it there for reference. But if that wasn't there, here is our data. We can see right away using the box and whisker approach that there's substantial overlap in all of these studies. And we can see that these are the really meaningful results from each experiment. And so our real result would probably be around here somewhere, which would be wrong. Okay. So in that case, a meta-analysis probably give us a speed of light somewhere around here, because that's where most of the studies are kind of clustered. The true speed's over here. So it doesn't always give us accuracy, but it gives us a way to summarize data. Right? So moving on to standard scores now. I mentioned that a standard score is also called a z-score, also called a z-statistic or a z-value or a normal score. All it is a number of standard deviations that your particular thing is from the mean. That's all it is. So it's a measure of how far a particular observation is from the mean of its distribution. For example, maybe I won't give you the mark that you actually get on your midterm. I'll tell you your z-score is this. You got 1.2 z's above the mean, which is really 1.2 standard deviations above the mean. You got to figure out what that means. Oh, it means I did better than 80% of the population, 84% of the population, which is not bad. I'm not that mean. I'll give you your actual mark, but maybe I won't. We'll see. I'll have to. Maybe I'll stagger it by a few days and let's just sweat for a bit. So the z-score only has any meaning if you know the parameters of the reference population. If you know the mu, which is the mean, and the sigma, which is standard deviation. So it's another measurement of relative standing, like percentiles. And here's a formula for it. Z is your value minus the mean divided by the standard deviation. Okay, so X is the raw score to be standardized, mu is the mean of the population, and sigma is the standard deviation of the population. Right now you're thinking, but these are the symbols for the parameters of the reference population of the entire university. And if we're talking about your midterm scores, why are you using these numbers? It's a conceptual thing. Whenever we write this down, we're saying that these represent the parameters of the superpopulation. But I can't really get access to the parameters of the superpopulation. All I can get access to is your numbers. So I'm going to plug in your standard deviation from this class in here. I'm going to plug in the mean from this midterm in here and pretend they're the parameters. So it's a conceptual distinction. When it comes to you doing the problems, don't worry about it. You're going to have exactly just one number to choose from, and you know which one it is. All right. So the equation is that again. Your number minus the mean divided by standard deviation. So in other words, it's the difference, the distance from your score from the mean standardized. This way we can compare different kinds of distributions. If I've got this class here, which is this wide, and this class here, which is this narrow, how am I going to compare if you did that far for the mean over here and this far for the mean over here? I got to compare them somehow. I compare them by dividing them by their standard deviations, and that kind of cancels out the width element of it. That's the logic of it. Okay. For example, here we got a mean of 100, standard deviation 25. Your z is going to be 1. That's like 1 standard deviation above the mean. Here, your z is minus 2. That's 2 standard deviations below the mean. Again, I'll give an example to show you how we do this and why we do it. It's a bit more obvious when we do examples. This is very useful when we're figuring out cutoffs for standardized tests, like the MCAT. medical admissions test, or the GRE, the graduate admissions test, or the SAT, the standardized admissions test in the US. So it allows us to calculate the probability of scoring a certain thing, assuming everything is normally distributed, and we always assume that. We often assume that, right? And it allows us to compare two scores from different distributions. For example, let's say you got a mark in this class, and you got another mark in, let's say, your biology class, and you want to figure out which class you're doing better in. It's going to depend on how hard the markers are in both classes and how dumb your other colleagues are in each class, right? So you're going to figure out your relative standing in each. And we're going to give an example just of that in a second. So we use this every year. The people who run these tests use the statistics to figure out what the cutoff is going to be for who we accept. Because we always want to figure out the percentile of individuals who are likely to get a certain mark. We're going to do an example. So here is the assumption of the MCAT scores in Canada. About 4%, about 90% of individuals fall within that 2 standard deviations, like I mentioned, 95%. So we know the LSAT score, by the way, is the law school admissions test. The LSAT score in Canada is normal. We know that because we're doing LSAT scores so many years now. Every year we have the data. Oh, look, it's exactly bell-shaped. The mean mark is 60, and standard deviation is 15, traditionally. So what's the lowest mark among those who are in the top 10%? Why do we care about that? We care about that because the law school people may say next year, we're only going to take the top 10% of students. That doesn't mean we're only going to take the people who score 90% and above, because maybe nobody scores 90% and above. Maybe the test is so hard that year that everyone gets like under 70 or something. Or maybe this test is so easy that everyone gets over 90%. In that case, the top 10% are going to be like those who scored 98 and above or something like that. So in order to make these cutoffs, we're asking, where is the cutoff, the lowest score for which only 10% get that and above? In other words, the 90th percentile. Okay, let's figure it out. Here is our formula. Remember, our z-score is x minus the mean over standard deviation. So the probability of that happening is 0.1, 10%, the top 10%. I look up this number. What's that number of 10%? It's 1.282. How do I know that? How do I know it's 1.282? There's actually a thing that I look up, the score calculator. If you go to, do I have a link there? I think I do. I should have a link. There it is, right. If I click on it, can I click on it and find it? It didn't work. All right. If you go to that website, there's a sample z-score calculator. These days we have calculators. In the old days we have tables that we look up. And on a test, I'll let you give you a table that you look it up on. Probably, we'll see. Or I'll give you the number, we'll see. So someone has done the work of figuring out a z-score corresponding to 10% on my distribution. Remember, here's my normal distribution. 10% top is over here. That has a certain number of standard deviations from the mean. It's exactly 1.282 standard deviations constitutes the top 10%. I plug that in here, I equate these two, and I solve for x. So, and I get x equals 79.23. So in other words, in this particular case of the LSAT, people scoring 79.23% and above are the top 10 percentile of applicants. And that's going to be the cutoff for which we accept law school admissions this year. With me so far? Okay, the hard part is looking up the Z that corresponds to 10%, equating it to our formula there, and just solving for x. So, the example I gave you a second ago, you're in 2 classes. Let's say you're in English and math class. You got 70% in English and 72% in math. And you're wondering which class you're doing better in. Why isn't the answer automatically you're doing better in math class? Because you got 72 in math and 70 in English. Why isn't it automatically math is better? Yep. The ranking might be different? What does that mean? Right. So maybe math is really easy. Maybe everyone's getting high marks in math. So depending on how you define which one you're doing better in, we're defining which one you're doing better in as how many of my colleagues I'm beating out. That's what I care about. Where's my ranking in the class? So here's the data. We know that in the class, in English class, the person got a 70, and in math class they got a 72. The mean mark for everyone in English class was 60. The mean mark for everyone in math was 68. The standard deviation in each class was that, 15 and 6. By the way, just look at it right now, you see that the means aren't that different, but here in English, it's much wider. It means there's a bigger splay. There's a much more variation in the kinds of marks people got. In math, it was a bit more focused, so almost everyone got the mean. So what we're going to do now is compute the z-score. That'll tell us the rank that this number was relative to everyone else in class. So, and the reason for that is each of these is from a different distribution. We're going to standardize the distribution by dividing by standard deviation. So here it is. The z-score for English is 70, the mark you got, minus the mean divided by the standard deviation, 0.67. The z-score for math is also 0.67. What does that mean? I got z-score of 0.67 for both of these. How do I interpret that? Yep. Same percentile in each class. You have the same rank in each class. You're doing exactly the same in each class. Okay. So a z of 0.67 suggests that the student performed 0.67 standard deviations above the mean in both class, which is like 70% above 70th percentile, around that. So it's doing equally well in both classes. So if we use a z-score calculator, we find out that this means that she's in the top 25% of each class. So like I said, 75% percentile. So again, this is how we read that. She scored 0.67. That's here. 0.67 is over there. So she's doing better than all of these people. 75% of the distribution she's doing better than in each class. So a couple of the concepts to remember. Central limit theorem, you hear a couple of times. All it is the assumption that under mild conditions, under typical conditions, most things have a normal distribution. So what I've been saying all along. Most human characteristics are distributed normally. Your marks at the end of all this will probably be distributed like this. Most people get something in the middle. A few have extreme marks. A few have really low marks. So under most assumptions, the central limit theorem tells us most things are normally distributed. I would click on this right now, but I can never get the computers here to work on it. It requires Java. If you click on this link, there's a little app that allows you to experiment with the central limit theorem. It randomly distributes points. If you sit there forever and you click on click, 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 and after some random distribution, you'll see that, oh my God, it starts being normally distributed because most random things are normally distributed. But it's not interesting enough to actually warrant doing it in class, so I won't do it this time. So as I mentioned, when you've got your curve here, here's your mean, here's your curve. One standard deviation is about 34% this way and 34% that way. So around the middle, 68% of all of your data is within one standard deviation. And again, 95% is around 2 standard deviations. You get to 3 and you get almost all of them, 99.7. This has a rule. This is a name for this rule. It's called the 3 sigma rule, or it's called, kind of boring, 68, 95, 97 rule, or the empirical rule. I call it the 3 sigma rule. The 3 sigma rule says that one standard deviation from the mean is about 68% of the data. 2 standard deviations is about 95% of the data, and 3 standard deviations is almost all the data. Anything more than 3, what's the point? You've got everything there. So when you're computing your z-scores, it's unlikely you're going to get anything more than 3 ever. Right? And it's summarized like that. These are the actual numbers. The probability of your score being less than the mean is about 68% and so forth. Doesn't matter. That's your homework, but before we get to it, is everyone clear? Kind of make sense? All right. Try the homework and it'll make more sense. Otherwise, we'll revisit this later. Cool. Thank you very much. Bye. Ooh, 4 viewers. Nice.